Let's look at the concept of floating, the types of floating, countermeasures, and the phenomenon of floating in bipolar transistors and MOSFET switching circuits and countermeasures for eliminating it. Floating means suspended in air, and you can guess that it is a very unstable state, floating on water or in the air. Inexperienced engineers or non-specialists often misunderstand that open pins of an MCU or IC, that is, not connected to anything, are 0 volts, but in circuitry, it is called a floating state. And it is a very unstable state. Of course, it doesn't matter if unused pins are open, that is, not connected to anything, but if a pin used as an input pin is open, that is, floating. There is a problem. The input pin is waiting to receive a signal, so if nothing is connected, a bunch of garbage values that are neither high nor low come in. That is, since the floating pin has high impedance. These garbage values come in continuously, and small external noise signals can also come in, and it is especially vulnerable to ME noise or surge noise. The floating phenomenon mainly exists in the MCU input terminal where the switch is applied, and depending on the type of applied IC. If the output terminal has an open drain or open collector configuration, a floating situation may also occur in the output terminal. Looking at the input side floating phenomenon, when the switch is opened, it becomes a floating state, and when looking at the input pin at this time, the input impedance is very large. So it becomes very sensitive to external noise or surges. In other words, it becomes an ambiguous state that is neither high nor low. Therefore, in these switching applications, to prevent the floating state, a pull-up or pull-down resistor must be connected to resolve the unstable input pin state. When we say floating, we often only consider input pins, but specifically, there is a floating situation not only for input pins but also for output pins. Of course, most output pins output signals to drive the next circuit or block, so in this case it is not floating. But if the internal configuration block of the IC is an open drain or open collector type circuit, it can be a floating situation depending on the internal logic. That is, if the input logic of the NMOS or NPN transistor is high, both turn on and the output becomes low, but if the input logic is low, the output terminals of the NMOS and NPN transistors are separated from the ground, becoming a floating state. In the open drain or open collector structure, when the input logic becomes low, both internal switches of the two elements become open and floating. The impedance seen at this time also has a very high impedance characteristic. This open drain or open collector structure is an output method used for interfacing when the voltage levels of the IC or circuit to be connected to the next stage are different. In other words, if the operating voltage of the MCU or IC is 3.3 volts, but the next stage circuit is a 5-volt system, if the voltage applied to the pull-up resistor is 5 volts, interfacing is possible immediately without a special circuit. This type of output is called open drain or open collector. Let's take a look at measures to resolve the floating state of input and output pins of MCUs or ICs. If one side of the switch is connected to ground and the switch is turned on, that is, if it is an active low input terminal, connect a pull-up resistor. Then, when the switch is not pressed, the default is high, and when the switch is pressed, the switch is turned on, which means it is an active high input terminal. Then, if one side of the switch is connected to VDD and the switch is turned on, that is, if it is an active high input terminal, connect a pull-down resistor. Then, when the switch is not pressed, the default is low, and when the switch is pressed, the switch is turned on, which means it is turned on. Depending on the MCU, it is possible to define an internal pull-up or pull-down programmatically, so in this case, it is not necessary to apply a pull-up or pull-down resistor. In an open drain or open collector structure, for a stable interface to the next stage circuit, select an appropriate VDD voltage, connect a pull-up resistor, and then connect it to the input of the next stage circuit. Since this circuit structure has an output structure that is inverted from the input, even if the IC to which the open drain or open collector is applied is 3.3 volt logic, if the VDD voltage connected to the external pull-up resistor is 5 volt, the inverted logic output of 0 or 5 volt is transmitted to the next stage circuit. On the contrary, if the IC to which the open drain or open collector is applied is 5 volt logic and the VDD voltage connected to the external pull-up resistor is 3.3 volt, the inverted logic output of 0 or 3.3 volt is transmitted to the next stage circuit. Whether it is an input or output stage, the pull-up and pull-down resistors should be 10 kilo ohms or more, and applying too small a value may result in high current consumption. In this way, the open drain or open collector structure is one solution to facilitate the circuit interface regardless of the supply voltage or operating voltage, and has the convenience of circuit design that allows you to immediately turn the load on and off by connecting a 5 volt load to the open drain and a 12 volt load to the open collector even if the IC operating power is 3.3 volts. As in the example, a similar device, the comparator, has an open collector output terminal, and therefore, regardless of the volts of the comparator operating voltage, any voltage and load can be connected and used to the output open collector terminal. This time, we will look at the standard switching driver circuit for an NPN transistor. Since it is an NPN transistor, it is a structure that turns on the transistor by the current entering the base to drive the load. Here, the resistance RB between the control output terminal of the MCU and the base plays the role of converting the control output voltage into an appropriate driving current. And since the MCU is complexly connected to the power supply and various devices, external surges or noises can be introduced and affect the base side of the transistor through the control output terminal, but this can be controlled to some extent by the series resistance RB. Generally, this series resistance RB applies a value in the range of several ohms to 1 kiloohm, and care should be taken because if a value that is too large is applied, it can interact with the internal capacitor between the base and emitter of the transistor and slow down the switching speed. In other words, in high-speed switching circuits, low resistance is advantageous if possible. The base and emitter of the transistor, i.e. the RE resistor connected to the ground, act as a pull-down so that even if the control output terminal of the MCU is floating, it is always held as a reference for 0 volt, preventing unintended and unnecessary voltage from being applied to the base side of the transistor, thereby enabling stable operation. The GPIO terminal of the MCU may be temporarily floating during transients such as when powering on, booting, or in low power mode. In general, it is recommended that this pull-down resistor RE be set at least 10 times larger than the RB resistor connected in series to the base side. If the RE resistor is too small, the driving current to the base of the transistor may be reduced, resulting in unstable switching operation. For example, if the RB resistor is 1 kilo ohm, it is recommended that the RE resistor be at least 10 kilo ohms. If you look at the actual related application data, there are many cases where there is no pull-down resistor RE, but it operates normally even with this configuration. This is because the base and emitter of the transistor have a PN diode equivalent structure, so even if the MCU control output terminal floats, a floating structure is not created between the base and emitter of the transistor. Let's look at the standard switching driver circuit for an N-channel MOSFET. This is a structure in which the NMOS is turned on by the voltage applied to the gate to drive the load. Here, The resistor Rg between the control output terminal of the MCU and the gate plays a role in converting the control output voltage into an appropriate driving voltage. And external noise or surge around the MCU can be introduced and affect the gate side of the NMOS through the control output terminal. But this can be controlled to some extent by the series resistor Rg. In general, this series resistor Rg applies a value in the range of several ohms to 1 kiloohm, just like a transistor. Note that if a value that is too large is applied, it can interact with the internal capacitor between the gate and source of the NMOS and slow down the switching speed. In other words, in high-speed switching circuits, low resistance is advantageous. The gate and source of the NMOS, i.e. the RS resistor connected to the ground, act as a pull-down, so that even if the control output terminal of the MCU floats, it is always set to 0 volts as a reference, preventing unnecessary and unintended voltage from being applied to the gate side of the NMOS, thereby ensuring stable operation. In terms of circuitry, the structure is such that it cannot float, but the reason why the control output terminal of the MCU floats is that the GPIO terminal of the MCU may be temporarily floating when turning on the power booting, or in low power mode. Generally, this pull-down resistor Rs is usually set to be 10 times larger than the Rg resistor connected in series to the gate side. If the Rs resistor is too small, the driving voltage to the gate of the NMOS may be low, resulting in unstable switching operation. For example, if the Rg resistor is 1 kilo-ohm, it is recommended that the Rs resistor be 10 kilo-ohms or more. One mistake that designers often make is not to apply the pull-down resistor Rs. In this case, the NMOS may heat up and be damaged due to its very unstable operating structure. And there is even a risk of fire in high-power driving circuits. This is because, unlike a transistor, when the MCU control output terminal is floating, the NMOS gate itself becomes floating. So a very unstable voltage that is neither high nor low is applied to the gate, and the NMOS randomly turns on and off, becoming uncontrollable and generating high heat, which can lead to its damage. Of course, depending on the designed product or system structure, if the MCU or driver IC has a structure where floating does not occur at all, it may work well without a pull-down resistor or Rs. However, since safety is the top priority, it is recommended to apply a pull-down resistor or Rs. This type of defect often occurs very rarely in the entire product. So it often takes a considerable amount of time to solve the problem in the field. If we look again at the circuit consideration when the pull-down resistor explained above is not applied, the NPN transistor is equivalent to a diode when looking at the base. So it is not in a floating state in terms of the circuit. Therefore, even if the control output side of the MCU is floating, the base side does not become a floating state. However, in the case of NMOS, the impedance is infinite when looking at the gate side, so it becomes a floating state, and if the control output side of the MCU becomes a floating state, the gate line itself becomes completely floating. Even without examining it in a complicated way with the concept of a semiconductor equivalent circuit. Even if we look at only the symbol of an NPN transistor itself, the base and emitter are connected by an arrow, that is, a PN diode. And the NMOS has an empty space between the gate and source with the connection disconnected. So it can be intuitively guessed that the transistor is in a non-floating state and the NMOS is in a floating state. In summary, the transistor base does not necessarily need to have a pull-down resistor, but the gate of either an N-channel MOSFET or a P-channel MOSFET must have a pull-down or pull-up resistor. The transistor switching driver circuit can operate normally with only the base series resistor, and the method of applying the standard pull-down resistor also operates normally. The RB resistor must be less than 1 kiloohm, and the RE resistor must be 10 times more than RB. when the NMOS switching driver circuit is driven only with the gate series resistor. The NMOS may be damaged by thermal runaway if the control output terminal on the MCU side temporarily becomes floating. Note that the circuit that applies the pull-down resistor operates normally. The RG resistor should be less than 1 kΩ, and the RS resistor is generally 10 times or more the RG resistor. The driving circuits of NPN transistors and N-channel MOSFETs apply pull-down resistors, but PNP transistors and P-channel MOSFETs, which have an opposite operating structure, require pull-up resistors. Likewise, it is advisable to follow the 10-fold rule for the ratio of series resistance to pull-up resistance. In other words, the RE resistance value of a PNP transistor should be set to 10 times or more of the RB resistance, and the P-channel MOSFET should be applied with an RS resistance of 10 times or more of the RG resistance. Thank you. Bye.